Welcome to my class on operators in quantum mechanics. In the last class, we have already studied the postulates of quantum mechanics, and in that, the second postulate was called operator postulate. It says that for every observable in classical mechanics, there is a linear Hermitian operator in quantum mechanics. That is, any measurable property in classical mechanics, that is mass, time, velocity, momentum, etc. All these properties are measurable, and these properties are known as observables, and corresponding to each of these property, position, momentum, velocity, kinetic energy, potential energy, all these terms are measurable properties which are known as observables, and corresponding to each observable in classical mechanics, there is a particular operator in quantum mechanics that we have already seen in postulate number 2. Then what is an operator? An operator is a symbol of a rule for transforming a given function into another function. For example, when we take a case in mathematics, we take the plus sign. The plus sign, if we put the sign itself, it has no meaning, but when it is coming in between two numbers, it shows the addition of those two numbers and giving the product. Similar to that, this operator is also a symbol. And by itself it has no meaning, but when it is present beside a function, it shows that this particular operation has to be carried out on that function to transform it into another function. Okay. So an operator is a symbol of a rule for transforming one function into another function. So it itself does not mean itself, but it has a meaning when it comes beside a function. So an operation has to be, each operator represents an operation that has to be carried out on a function to transform it into another function. Usually operators are denoted by an alphabet, capital letters, with a cap symbol on the top. Cap symbol on the top. For example, energy, total energy of a system is represented by an operator known as Hamiltonian operator, which is represented by capital H and a cap symbol on the top. Okay. Now we'll see the major types of operators in quantum mechanics. That is, these are the observable properties, and these are the expression for observable properties in classical mechanics. Then we represent a operation of the function and symbol for the operator. These are the operators, and each operator represents an operation that has to be carried out on that particular function. So first simplest observable is momentum, and we know that momentum is equal to mass into velocity, and that it is represented as small letter p, and symbol for it is px, and this x represents a single dimension. If it is representing a three-dimensional space, then it has to be represented by three directions x, y, and z. So here px represents it is a momentum along the x direction only, and the operation that has to be carried out on this is minus I h cos into dou by dou x. That is the operation that has to be carried out in order to get the momentum of a system. Okay. Then second one is kinetic energy. Kinetic energy is represented in classical mechanics by either T or Ke. It is represented here. It is represented by capital T. It is given by the equation half mv square, where v is the velocity. And corresponding to kinetic energy, we have the symbol E cap, kinetic. And the corresponding operation that has to be carried out is represented by this function, minus h cos square by 2m into dou square by dou x square. This is also in a single dimension. If it is three-dimensional, then we have to take it in both x, y, and z directions. Then position. Position is represented by the symbol x, and it is represented by the operator x cap. Then potential energy in the classical mechanics, it is represented by capital V of x. In quantum mechanics, it is represented by the operator E cap potential. Total energy of the operator is of a function is represented by the sum of the kinetic energy and potential energy. Kinetic energy we have already found it as, potential energy already found. Then the sum is represented by an operator represented by capital H, which is known as the Hamiltonian operator. That is, this is the particular operation that has to be carried out. This is the sum of kinetic energy plus potential energy. It gives the total energy, which is represented by Hamiltonian operator. Then another measurable property is angular momentum, which is represented by Lx, Ly and Ls. Lx represents, it is the angular momentum along the x direction. Ly shows the angular momentum in the y direction, Lz in the z direction, and the total angular momentum is capital L cap, which is the sum of small lx plus small ly plus small lz, and each operator is having this particular operation. And when we represent the total angular momentum in a three-dimensional space, we have to sum all these three single direction angular momentums. So these are the commonly known observable properties and their quantum mechanical operators. So for every function, every measurable property, there is a symbol in quantum mechanics which represents a particular operation that has to be carried out on the system to transform it into another function. Okay. Then it also says that the postulate number 2 says that for every observable in classical mechanics, there is a linear Hermitian operator in quantum mechanics. And what do you mean by a linear operator? If an operator is linear, if it satisfies these two functions, these two equations, that is, for addition, if a cap is the operator, if a cap is acting on f plus g, f and g are two functions, then it is equal to a cap of f plus a cap of g. If it satisfies this condition in addition, then a cap is a linear operator. Similarly, for multiplication, c into f of a cap is equal to c into a cap of f. If these two conditions are satisfied by an operator, then it is called a linear operator. For example, we consider two functions d by dx and square. D by dx is a linear operator because it satisfies this condition. These two conditions are satisfied by d by dx. But square is not a linear operator because this condition is not satisfied by square. That is, square of sum of a function is not equal to sum of the squares of these two functions. Okay. Hermitian operator. So a function, an operator is said to be a Hermitian if it satisfies this condition, that is, integral psi star a cap of psi should be equal to a cap of psi into psi star into psi. That is, psi star represents the conjugate, complex conjugate of the function. If it is a complex function, the complex conjugate is taken and it is multiplied by a cap of psi. That is, psi is acted upon by a cap operator, then it is multiplied by psi star and it is integrated. If it gives same result as this one, then we call a cap as a Hermitian operator. Okay. So if an operator, for almost all the operators will be linear operator or an Hermitian. So for corresponding to each observable in classical mechanics, there will be an operator which will be linear and Hermitian in quantum mechanics. This is another important operator we have already discussed, Hamiltonian operator. It gives the total energy of a system. It is the sum of the kinetic energy operator and potential energy operator. Kinetic energy expression is this, potential energy expression is this. So total expression for the Hamiltonian operator is this one. Another important operator is a Laplacian operator del square. Del square is the sum of these three functions, that is dou square by dou x square plus dou square by dou y square plus dou square by dou z square in the three dimensions. So it is generally represented as del square, which is known as the Laplacian operator. These are operators which can be applied when we write the Schrodinger wave equation. So these are the major operators that we study. So an operator is a symbol which represents a function or an operation that has to be carried out in a function to transform it into another function. Thanks.